Hello friends, I welcome you all in this course on fundamental of engineering physics. I am Dr. Mohan L. Verma and today's topic is the fundamental of nuclear physics. Although nuclear physics is a wide subject of physics and to cover one single lecture all the components it is very difficult. So, here I am just giving some fundamentals of that nuclear physics. So, I will start from the basic structure of atoms which consists of that electrons, protons, neutrons, and then I will move to the structure of nucleus and the components of that nucleus as well as that properties of nucleus. Then further I move from that the basic concept of this the structure of nucleus to some phenomena concerned with this nucleus, its stability and some properties like nuclear fusion, nuclear fission, and that application of these two special phenomena of that nucleus, that is the fusion and fission. So, the objective of this lecture is to introduce the structure of atom and nucleus and then to impart knowledge on the properties of nucleus and to give comparative analysis of these two phenomena, nuclear fission and nuclear fusion, and to discuss about the application of nuclear energy. This is very powerful energy and the need of a future. And outcome of this lecture, so this topic enable learners to understand the basic concept of nucleus and the nuclear reactions and how to generate nuclear energy and apply safely in daily life events and learn some fundamental mathematical formula to solve properties of atoms and nucleus. So, let us start with this atomic model. So, actually we know about that atom. This is actually that the end of that 19th century it was considered that as that elementary part of any material. So, that was atom, and after that invention of that electron by using that J.J. Thomson's experiment and that calculation of E by m, we know about that electron, and then that basics of that material, this moves to that that electronic level. And at that time it was after some experiment it was thought that that atom contains that electrons and protons, and in that the beginning of that 20th century we know about that neutrons. But the question was what is actually that structure of atom. So, some models were given by different scientists, and it was started by J.J. Thomson. So, this is known as J.J. Thomson's model, and that is also known as watermelon model. And in this model, these atoms are visualized as the homogeneous sphere which contains uniform distribution of positively charged particles, and that negatively charged particles, basically that is electrons, these are embedded in this on this like seeds in the watermelon. And the main drawback of this model was all these charges are assumed to be at the rest, and when we use that the classical electrodynamics, then we know that no stable equilibrium can be exist in electrostatic configuration. So, then we one more model, it was proposed after this Rutherford's experiment, and this is one of the famous experiment in 1911, and this Geiger and Marsden, these are that students of Rutherford, they performed that well known experiment, that is alpha particle bombardment on that gold foil, and several a list of several observations are there, and on the basis of that observations by this experiment, Rutherford proposed that an atom, this has a lot of empty space and it contains a tiny matter at its center, that is known as nucleus, and whose size is of the order of 10 to the power minus 14 meter, and that it is compared as far as that ratio of that the size of nucleus as well as the size of that complete atom in the form of that ratio. So, for the comparison it was just said that if there is a football ground and at the center, if one that football is placed, then the size of football, that is actually the nucleus, and the boundary it is considered as the atom. So, the nucleus is actually positively charged, and most of the mass of atom is concentrated in the nucleus, and this nucleus it is surrounded by negatively charged electrons. So, this is that model given by Rutherford. And he also suggested that these electrons are not at rest, but it is moving around that nucleus in a circular orbit. And but this model also fails, and the reason is it is just failed to explain the distribution of electrons around the nucleus and also the stability of the nucleus, because according to classical electronics, any isolated charge should emit electromagnetic radiation continuously, because that electron, this is negatively charged, it is moving in a circular path, means it is isolated electron. So, this will actually generate electromagnetic radiation, and this electromagnetic radiation is actually the form of energy. So, this will lose that energy, and after certain state of time, by following one spherical path, this will just fall into that nucleus. So, it can no longer sustain that circular motion. Then after this failure of this Rutherford model, one more model that was given by Niels Bohr in 1924, that this electron is in an atom, this move around the nucleus in a circular orbit, but that circular orbit not similar to that Rutherford's model, but this is under the influence of Coulomb electrostatic force of the attraction. So, these electrons in an atom revolve around the nucleus only in certain discrete orbits. So, here that is not the simple, this is actually that discrete orbits, and these discrete orbits are stationary orbits, and which is further considered that energy levels, and electrons in such orbits this do not radiate electromagnetic energy, because these are in that discrete orbits, and that is a stationary orbit, and these orbits, in this orbit, that angular momentum of electron, these are actually quantized. So, the first time this quantization or quantized term is used by Niels Bohr, and according to him, that that angular momentum of that moving electrons in that circular orbit, that is actually the integer multiple of h upon 2 pi, and that n, mathematically it is written as equivalent to mvr is equivalent to nh upon 2 pi, and this h upon 2 pi, it is further considered as h cross, and here this n is known as a principal quantum number. So, depending on that different types of motion of that electrons in electronic physics, this quantum numbers is classified in chemistry and different part, but here in the basically that is mvr is equivalent to nh upon 2 pi, where n is a principal quantum number, and h upon 2 pi, it is further denoted as h cross also. So, on the basis of this model, this several phenomena like that is spectral analysis, that hydrogen spectrum, and that line spectrum, and other analysis can be considered, and here that transfer of energy means, although these electrons are not emitting electromagnetic waves, but it can emit energy when it transforms from one energy level to another energy level, and that transfer or absorption of energy, this depends on that direction of transition. When that electron, it moves from lower energy level to higher energy level, then it needs to absorb energy, and when it jump from higher energy level to lower energy level, then it will emit that radiation or that energy. So, on the basis of this theory, that the phenomena like that laser and that phenomena like that hydrogen spectrum or line spectrum, this can be explained easily. Now, the main part, that is the composition of nucleus. So, let us focus on now the nucleus, because this is related to that nuclear physics. So, atom have obviously that nucleus which is surrounded by electrons, and this nucleus actually contains protons and neutrons, and from our school days we are studying these, and these neutrons, these are electrically neutral. So, the charge on that electron is equivalent to 0, and protons inside that nucleus, this has positively charged. So, generally that the charge is taken as positive E. So, charge is equivalent to the charge of electron, but sign is positive, and the number of protons, this is called as atomic number. So, in the basic chemistry it is given, and the number of neutrons, it is called as neutron number, and the total of this neutron and proton in the nucleus, that is called as mass number, and it is represented by capital A. So, A is equivalent to Z plus N, and these two constituents of nucleus, that neutrons and protons, these are collectively known as nucleons. So, if somewhere it is written as nucleons, means we are considering that is the total number of protons and neutrons, and the general notation for the any nuclei, that is X, A, Z, where A is an upper part and Z that is atomic number, that is at the lower part of this symbol X. So, depending on this the Z, A on different elements, that materials are classified, or that elements are classified in the different parts, just like isotopes, isobars, isotones. So, what are actually these terms, isotopes, isobars and isotones, and how it differs from each other, let us see. So, actually these isotopes, these are the atoms of the same element having same atomic number Z, but different mass number A. So, for example, that hydrogen has 3 isotopes, we can take that one is that simple hydrogen, it is 1H1, and the second one is that deuterium, that is 1H2, and the third one is that is tritium, that is 1H3. So, these are 3 isotopes of hydrogen. So, these isobars are the atoms of different elements having same mass number. So, in the first case, in the case of that isotone, that same atomic number, but here this is same mass number A, but a different atomic number Z. So, that here that there is not it is not required that is the same elements, but that elements may be different, but having same mass number and with different atomic numbers. Some examples are here we are giving, that the sulfur, chloride, argon, potassium, and that this calcium. So, this here that atomic numbers are differ, that is 16, 17, 18, 19, 20, but that atom that the mass numbers A, that is equivalent to 40. And isotones, these are actually the atoms of different elements having same numbers of neutrons. So, here that examples are that boron, carbon, and these are isotones. Here its total number of neutrons are N is equivalent to 7. So, now let us move to some properties of nucleus, but before going to the details properties of nucleus, we must know about one unit that is basically used in nuclear physics, that is atomic mass unit. So, that the mass of nuclei, the reason is the mass of nuclei is very small, and therefore, it is more convenient to express it is in terms of that unit, and which is known as atomic mass unit, and somewhere it is represented as AMU or just U, and mathematically it is defined as the 1/12 of the mass of isotopes of carbon, and that carbon isotope is C612, and generally this isotope is used because it is abundant in the nature and easy to available. So, we can calculate its that this unit, that is atomic mass unit, is equivalent to mass of this carbon atom divided by 12. So, that 1 U, it is equivalent to 1/9926 into 10⁻⁻26 by 12. So, after calculating, that is equivalent to 1/660 into 10⁻⁻27 kg. Mathematically, this can be compared with the mass of protons or mass of neutrons. So, somewhere when we consider that mass of protons or mass of neutrons, so that is taken as equivalent to 1 AMU or 1 U. So, let us discuss about the size and the density of nucleus. So, in general, we consider that nucleus as a spherical shape. So, that all these protons and neutrons, these are homogeneously distributed in that nucleus of this spherical shape. So, we can calculate that the density of this nucleus. So, that first we have to calculate the mass of nucleus. So, the mass of nucleus, that will be obviously that mass of protons and mass of neutrons. So, how we will calculate that? We will first count that how many numbers of protons are there and how many numbers of neutrons are there, and then by multiplying its mass with one single neutrons and single protons, and we can add and we can get the total mass. And for the density, so density, that the volume of nucleus, it is just a spherical shape. So, we can use that 4 pi by 3 pi r cube, and here we use one term, that is r, that is the size of this nucleus, and it is also considered that this size r, it is actually, it depends on that A, that mass number A. So, this is R, it is proportional to a to the power 1 by third. So, here this R naught it is taken as a constant, and this R naught is equivalent to about that 1 upon 2 Fermi, and here one another unit, that is the fermion or Fermi, is used, and this Fermi, that is equivalent to 10 to the minus 15 meter. So, by considering all these parameters, we can calculate the density of this nucleus, and that is actually in the order of 10 to the power 27. Okay, so density of this nucleus, that is calculated up to 2.3 into 10 to the power 17 kg per meter cube. So, what we can conclude that this nuclear density is actually independent of mass number A, as well as this is a very compact structure. So, here this formula that R, it is equivalent to R naught A 1 by 3, which we just used for to calculate that density, and this formula is only applicable when this Z, that atomic number, it is greater than 10. This is the condition for the use of this, and this R naught, it is in as an average taken as 1.2 F, and this F, this is that another unit, it is actually named after Enrico Fermi. Now, some more parameters. One is this mass defects and binding energy. So, before going to this, just I am just summarizing some properties. First one is we can calculate the mass of nucleus, and that mass of nucleus is the mass of the sum of mass of protons and mass of neutrons, and we can calculate that radius of that nucleus, and that radius of nucleus, that actually follows this rule that this R it is actually proportional to a to the power 1 by 3 with that constant R naught, and by using these two we can calculate the density, and that is in the order of 10 to the power 17. So, this is a very compact structure. Now, let us deal with two more parameters, that is the mass defects and the binding energy. So, it is experimentally found out that the mass of this nucleus, it is always less than the sum of the mass of individual constituent particles. So, initially we have calculated that the total mass as the sum of that the mass of constituent particles, protons and neutrons, but experimentally it is observed that the total mass, it is less than this the sum. So, for example, in this carbon nucleus C12 this expected mass of that nucleus, that will be equal to this 6.05196 U plus that the total number of protons, that is 6.04362 U, that is equivalent to 12.09558 U, but the experimentally that atomic mass which is found at is equivalent to 12 U, because on the basis of this mass of this stable carbon isotope, we have calculated or we have defined that atomic mass unit. So, this is actually equivalent to 12 U. So, there is a difference between this the experimentally observed mass as well as along with this the mass calculated by its constituents. So, this mass difference, this is denoted by delta m, and here it is calculated as equivalent to 0.09888 U, and this mass difference is actually called as mass defect. So, mathematically for all the elements, all the nucleus, we can calculate this mass defect by using this formula, delta m is equivalent to Z multiplied by MP plus n multiplied by Mn minus m. So, here this Mp, it is the mass of protons, Mn, this is the mass of neutrons, and Z we know this is total number of protons, and n is the total number of neutrons, and this capital M, it is actually showing the mass of nucleus, that experimentally observed mass of nucleus. Where has this mass actually disappeared? This answer was actually provided by Albert Einstein with his this mass energy relation, and we know this is a very famous relation, E is equivalent to mc square, and after this relation we can have this this mass can be converted into energy, and energy can be converted into mass. So, according to this relation, the mass can be converted into energy, and this relation is called as binding energy. So, this binding energy will be equal to that mass defect. So, in spite of that mass, when we replace this m with delta m, that mass defect, then we will have that binding energy. So, mathematically what we will have, this B is equivalent to ZMP plus ZMN minus capital M, multiplied by c square. C is the speed of light, so that is 3 into 10 to the power 8 meter per second. Anywhere if we want to calculate binding energy, we can use this formula, and this is applicable for all the nucleus. So, we have one binding energy curve, and here this in this curve this binding energy is calculated in terms of binding energy per nucleon. So, per nucleon means total number of protons and neutrons. So, that total binding energy is calculated by using this formula. So, ZMP plus N ZNMN minus M multiplied by c square by this A, and this is that plot which is actually used to show that stability of that nucleus. So, initially before that this energy in the lower side of that atomic numbers or mass number, it is very less for hydrogen, helium type of things, and it moves up to increases up to that ferrous, and it starts decreasing. So, as the binding energy is highest means it is more stable, and if it moves from this highest value to lower energy means its stability is decreasing. So, what we can say? So, that ferrous where its binding energy is about 8.8, the iron, it is more stable. When we move right to that iron and or left to that iron element, then this binding energy decreases, means its stability decreases. So, in the lower side that hydrogen, helium, these are less stable elements, and in the right hand side at that higher value of that atomic number, that is uranium or other elements, these are unstable elements, and even that alpha particle, beta particle, gammas are radioactive properties. These are observed in this high value of A, that elements of high value of A, and also that all that nuclear phenomena that is concerned with this that uranium and plutonium type elements, because these are unstable nuclei. So, this nuclear force, so nucleus of this actually atoms, as we know, that contains protons and neutrons, and also we know that protons are positively charged, and from electrostatics we learned that this like charge actually repels each other. So, if we calculate that electron, that protons inside that nucleus, and we know that the maximum size of that nucleus is in the order of 10 to the minus 15. So, by using that Coulomb's formula, F is equal to K multiplied by Q by R square, when we put the charge of that proton as well as that distance as 1 Fermi, then the force, electrostatic force between two protons, that will be equivalent to 230 Newton, and this is high enough. So, what it should be, it just come out of that, it should be that proton should be come out of that nucleus because of this high force between two protons, but it is in form of that compact nuclei of the density of 10 to the power 17. And why it is so? Because obviously there will be some attractive force, a strong attractive force more than this, and that attractive force is actually that nuclear force. So, that nuclear force actually it is binding all these nuclear all these protons and all these neutrons, avoiding this repulsive force, that Coulombic force between among these protons. So, this attractive force which holds that nucleus together, and it is called that strong nuclear force. It is not ordinary, this nuclear force that is very strong, and these properties of nuclear force, this is well understood through various experiments, and these experiments were carried out in between 1930 to 1950s. So, some properties of this nuclear force, we can say that nuclear force, this is very short range because that the size is very small, acting only up to the distance of few Fermi, and the second, the nuclear force is attractive and acts with an equal strength between proton, neutron and neutron. So, that will be equally applied between this pair of that nucleons, that is proton, neutrons and neutron. And this nuclear force does not act on the electrons. So, it does not alter the chemical properties of atoms, because these electrons are outside of that nucleus. So, this is not acting on that electrons, and electrons are actually responsible for all chemical properties. Now, some phenomena concerned with that nucleus, and one of that phenomena is nuclear fission. So, in 1939 German scientist Otto Hahn and Strassmann, they have discovered that when uranium nucleus, this is unstable nucleus as I mentioned in because its binding energy per nucleon is much less than with compared to iron, is bombarded with the slow neutrons. So, it breaks off into two smaller nuclei of comparable mass with the enormous amount of energy. And the process of breaking up of the nucleus of a heavy atom into two smaller nuclei with that large amount of energy, it is called as nuclear fission. And there are certain equation that is known as fission equation. So, here one of the stable equation, that reaction I am showing here, that is uranium, that is the one isotope, that is 235, it is just absorbing one neutron and it is converted into another isotope of that 236, and then it gives two lighter elements like barium and krypton with 3 numbers of neutrons plus that Q, that is that energy value. So, this is schematic diagram of that nuclear fission, and in order to calculate that energy Q given in that equation, what we will do? We will calculate the total mass, means finally we have to calculate that mass defect. So, we will calculate the total mass of reactants and then the total mass of product. So, in the reactants we have that uranium and that neutron, one single neutron, that is the slow neutrons, and in the that product we have 3 neutrons with 1 barium and krypton, and we can have its mass, and we calculate the total mass, and by just calculating its difference, we can have that mass defects or the change in mass, and by calculating with by multiplying this with C square, we will have that total energy. So, generally when we convert that 1 AMU in energy, then we get about 931 mega electron volt energy. So, from one single fusion we can calculate that we will get about 200 mega electron volt energy. So, this is that the energy released by one single reaction in nuclear fission. Then this nuclear fission actually converts into chain reaction. How this will? Actually, we are using one slow neutron and one uranium, it is now creating 2 light nuclei, and along with that light nuclei of barium and krypton, in that reaction we have 3 neutrons are there produced parallel to that. So, that 3 neutrons will further interact with 3 uranium 235, and again that 3 uranium will give 3 more neutrons. So, in the multiple orders numbers of neutrons will increase. So, in first case it was 1, in the second step there we have 3, that it will generate now 9 neutrons, and then further this will generate about 27 neutrons. So, in this order the number of neutrons will increase, and simultaneously that reaction will increase. So, this type of reaction is known as chain reaction. So, if that neutrons are not being controlled, that will be one infinite reaction. So, this chain reaction is actually classified into 2 parts. One is that uncontrolled reaction and controlled chain reaction, and this actually depends on that the controlling of that neutrons generated during this reaction. So, in uncontrolled chain reaction the numbers of neutrons multiply indefinitely at the entire amount of energy is released in the fraction of second, and one of the example is that in the atom bomb. So, and if this chain reaction is controlled, it is controllable, then we can harvest this amount of energy for our needs, and it is used in our controlled that nuclear reactor. So, that nuclear reactor, that energy generated by this nuclear reactor is useful because this is controlled one, and this atom bomb is so harmful because it is uncontrolled. So, now one of the application of this nuclear physics, that is very important application, that is obviously that nuclear reactor. So, this nuclear reactor is actually the device which actually use that nuclear fission reaction inside, and in self sustained controlled manner, and then this energy is produced which is either used for that research purpose or for the power generation, and this first nuclear reactor, this was built in the year of 1942 at Chicago, USA by Enrico Fermi. That is why that fermion or Fermi term is used, name after him. And this main part of actually this nuclear reactor is concerned, then obviously it is fuel and some moderator, because to control or moderate this reaction, and control rod. And in addition to this, there will be that cooling system and some connected power generation setup. So these are some basic parts of that nuclear reactor. So as a summary, we know that the nucleus of element X having this atomic number Z and the mass number A is represented by X, A, Z, and this empirical relation between the radius of nuclei, which is applicable only when Z is greater than 10, and that is this R, it is proportional to A to the power 1/3. So this R is equivalent to R naught A upon 1 upon 3, where this R naught is equivalent to 1.2 F. And this density of nucleus, this is the mass of that nucleus upon the volume, it is calculated as equivalent to 2.3 into 10 to the power 17 kilogram per meter cube. So this is very compact sphere, and if M, capital M, is the mass of the calculated, that experimental mass of that nucleus, MP and M, and these are the mass of protons and neutrons respectively, then we can calculate mass defect is equivalent to the total mass of this nucleon minus the experimental mass, and this binding energy can be calculated by using this binding energy and this mass defects multiplied by C square. And this average binding energy per nucleon, this is maximum for iron, it is 8.8 mega electron. If a heavier nuclei decays into lighter nuclei, it is called as nuclear fission, and if two lighter nuclei fuses to form heavier nuclei, it is called a nuclear fusion. And in the nuclear reactor, the nuclear chain reaction is controlled, and in stars the energy generation, that is only through the nuclear fusion, where hydrogen is converted into helium in general.